Thanks, Annie, for the introduction, and thank you everyone for coming. And as Annie said, I am Rohit. I'm a PhD student at CMU, and today I'll be talking about some of the work I've been doing towards the later part of my PhD. I'm just specifically focused on trying to understand people in images and videos, and specifically trying to do that by using the context around them. So typically parameterized by the scenes and objects in around the people. All right. So before we start talking about my methods, let's first try to see why do we even want to understand humans. And I think the simple answer is that most AI systems will either coexist with humans or assist humans, and in either case, they need to understand humans to be safe around them. For example, if I show you this video of a car driving down the road, car driving down the road, we see a couple walking on the left, a child walking on the right, and suddenly we see the child decides to run across the road towards his parents. And in this case, it was a human driver who was able to anticipate this and sort of slow down and stop in time to be safe around the people. Cars of tomorrow would be driven by autonomous agents, and they would need to be equally safe around people. So part of that would require understanding the actions that people are doing. So for example, the couple in the left are walking and sort of looking at their child. The child is looking at and sort of starting to run towards his parents. And using that, we ideally also want to be able to predict their intentions, that the child might decide to sort of rush towards his parents. And using that, we want to sort of have our planner sort of plan for such possibilities. And of course, this is not limited to autonomous cars. Pretty much any system that interacts with humans would need to understand them. So that includes sort of caregiver robots, so robotic systems helping the elderly and need to identify if somebody has fallen to help them get up, or assistive applications like applications assisting the blind people, sort of trying to understand the actions that their companions are doing. And also for sort of downstream learning or robotics tasks like imitation learning, where you want to teach a robot to do certain actions by following what a human is doing. Now, human understanding can be thought of at a few different levels. So as there was this very nice study from Barker and Wright back in 1954, which sort of tries to sort of think about human understanding at different levels of temporal hierarchy. So from like very small sort of short atomic actions like stepping down from the curb or sort of crossing the street or walking to the school, towards like even towards long-term actions like sort of getting an education and climbing to the top in life. So basically human understanding can be thought of at all of these different levels, but as you can imagine, recognizing all of these from like short images or videos is not always possible. So a lot of the work that I'll be talking about today would sort of focus on these more atomic level human understanding, sort of more things that you can try to understand from, let's say, body motions or like people moving, like short videos and images. And now that we are trying to understand people from short body motions, the first obvious solution is, why don't we try to use the human pose? And in fact, that there has been quite a bit of work in trying to recognize human actions by looking at pose. So for example, this is an experiment from Johansson et al. Back in 1973, which shows that just by sort of putting light markers on people's sort of joints and just looking at that over time, we are able to recognize a lot of actions. So for example, I'm sure everyone here can recognize actions of like cycling, jumping jacks, crawling, and walking. But this quickly gets hard. So for example, if I show you this video or this video or this video, it clearly is much harder to recognize what action here is going on. So for example, the first one is chopping wood or something, drinking, and then drawing. On the other hand, if I actually show you the scene context, so for example, in this video, we can pretty much hide out all the pixels that belong to the persons, and just by looking at the objects in the environment state, we can easily recognize what action is going on. And so basically, scene context makes action recognition a lot easier than just looking at the person. And that is sort of what the key insight is of all the work I'll be talking about today, that a lot of human actions are very readily recognizable from the state of the person's environment, which we typically parameterized by the scene and objects, apart from, of course, their own state, typically parameterized by the pose. And I've tried to use that. I've tried to exploit this this dependence in a few different ways. I'm talking about 3 specific ways where I've tried to use this context towards human action recognition. And the first part of this talk will focus on using this context for recognition. So the setup here is that you are given a video or an image, and you want to recognize what is happening in that image or video. So for example, you're seeing people doing a bunch of actions, and you want to sort of label all these actions. And this can be done at sort of a global level where you want to label the whole video into one of K classes, or you can also think of it at more fine-grained level, like recognizing what each individual person is doing. So that will be sort of the first part of this talk. Next, I'll try to take a step further and try to predict what can happen in an image. So in the first case, we were trying to recognize what we are actually seeing is happening in a video. In the second case, let's say I just give you an image of a scene with, let's say, a sofa in it. One can possibly predict that somebody can, for example, sit there, or if there's a hallway, somebody can walk there. So that's sort of also known as affordance understanding from images, and that will be sort of the second part of my talk. And finally, in the last part, I'll try to move towards longer-term temporal context. So in the first two cases, we'll be looking at sort of short-term temporal context in like images or like short video clips. In the last part, I'll try to sort of motivate the actual thing that you get with videos is a long temporal dimension, and how we can try to move towards actually exploiting that. All right, so with that, I'll start with the first one. All right, so action recognition is obviously not a new problem. A whole lot of PhDs have been done on that. And a lot of previous work has been sort of focused on what's typically referred to as trimmed action classification. So you're given a video clip and you want to classify it into one of K classes. So for example, a clip like this would probably be classified into, let's say, kissing. But obviously, videos are a bit more complex than that. You have multiple different actors doing different actions at any given point in time, and you ideally want to recognize all of those actions at any given time instant. So for example, here the woman is initially sitting and listening to the person, and eventually kissing, and the man is sitting, driving, and singing. So each of them are doing a whole bunch of actions at any given point in time, and ideally we want to recognize all of that. And this is technically known as the problem of spatiotemporal action detection, where the task is that you want to localize actions in space and time. So given any frame, you want to recognize all the people in that frame and recognize all the actions that they're doing. So detect the people and recognize all their actions. And the setup is actually very similar to object detection. So you can pretty much use the same sort of evaluation metrics. So frame MMP, for example. And I'll be sort of working with this recently proposed dataset called AVA, which came out from Google last year, and is actually the perfect test bed for something like this. All right, so initially, let's start by building sort of the baseline architecture for this task. And since this is sort of very similar to object detection, so we can basically start by extending standard ideas from object detection towards video action recognition. And basically, I'll be following sort of faster RCNN paradigm and just extending that to deal with videos. So now that we have a video clip, so instead of having a single frame to recognize objects in, now we start by taking a short clip. So the key frame that we are trying to recognize the actions in, and a few frames of context around it. We pass it through a convolutional network. Since this is a video, so we use a 3D convnet. Typically in faster RCNN, you'll use a 2D convnet like a ResNet or something, and you get like the spatiotemporal feature blob with the time, with this being the time dimension. Oops. Anyway, so from the feature blob, we extract out the center frame's features. So basically, just slice out the center frame and pass that through a region proposal network. So that's again very similar to faster RCNN, and that gives us a bunch of proposed boxes in this keyframe of where the people can be. And then for each of these, we can sort of extend them in time. So we ideally, since we have the time dimension as well, so we want to try to sort of also encode the temporal aspect of these boxes, so we can extend them in time. And note that this is obviously an approximation. Like people could have moved a little bit over the short video clip, but we assume that in the short video clips with high frame rate videos, people don't move that much, so we can assume that they just moved along a tube. And using these tubes, we can use sort of a spatiotemporal ROI pooling operation, which is basically just extracting out features corresponding to these tubes from the spatiotemporal feature map, and sort of concatenate that into a feature representation for the person. And then we can pass that through sort of what's called a head network, which is another convolutional network that takes these features corresponding to the person and does bounding box regression and classification. So all of this is actually very similar to faster RCNN, and the only thing that I've changed is really just adding the spatiotemporal ROI pooling and just replaced all the convolutional networks with 3D convolutional networks.
Question.
Yes?
Does the bounding box regression regress different bounding boxes in each frame to account for motion between frames?
No. So bounding box regression is still at like the keyframe level, because the way the task is defined is that you're only trying to recognize the boxes in the keyframe, And the only reason we are stretching in time is just to capture some amount of context. And yeah, so the tubes, we are not really evaluating if the tubes are good or not. All right, so this initial baseline we actually submitted to the ActivityNet challenge last year, and as Ani said, it's worked pretty well. It got the second position, and we're actually pretty close to the first position as well. And this was a completely RGB only model without any ensembles. Yeah.
If you just do fast RCN, but you don't do context, how does this perform?
So there are so the original paper did have that baseline. Their numbers were really bad, around like 15% or something. But I think part of the reason is they didn't implement it properly. We didn't actually compare. We didn't actually do an analysis for our method. But I think there would be some improvement with the temporal aspect. Okay. All right. So this works pretty well, but we haven't actually used any context so far, except from, of course, the little bit of receptive field that comes in through the into the ROI pooled features. And as you can see, context is actually quite important. For example, if you were to recognize this person's video, with this person's actions, which is actually labeled as listening to a person, that obviously is predicated on the fact there is another person in the image. So you want to be able to look at that and not just the actual person who you're trying to recognize. And also, like watching a person is again predicated on the fact that there is another person in the video. And in fact, the next model I'll talk about, which is basically an extension of what I talked about earlier, learns to do that automatically and or learns to do that. And these are actually some sort of attention maps that we can extract out of our model that I'll talk about. And it learns to sort of focus on the other people in the image, the objects in the image, and uses that to recognize the person's actions that we are interested in. Okay, so this is so our solution for that is basically what we call person-specific self-attention. So the idea is that since we are trying to recognize a person's actions, we use that person as a means to query sort of parts of the video that are useful for recognizing that person's actions. And this is actually an idea very similar to the transformer network, which was used in Attention Is All You Need from NIPS 17, and also there were some other related works in this direction, which have also shown some positive results. All right. So the setup here is that the initial part is pretty much the same. So we have the ROI pooled features, which basically give us what we call like an initial actor representation. So ROI pooling will basically extract out this feature corresponding to the person, which is what our starting point is. And we have the full video feature. So this is the spatiotemporal feature map we get from passing the full clip. And now what we do is we take the full feature map and project it into what these key and value features. And basically these are basically just linear projections of the original video feature. Now what we can do is we can take the actor representation and we do a dot product attention over the key features and use that attention to do a weighted sum of values. So you can think of it as like a key value lookup where you use the initial representation to sort of find out which regions of the context are important and use those to do a weighted sum of the values and sort of add it back to the original representation, pass it through a few more layers and get an updated actor representation. So sort of at a block level, you can think of it as basically, we call this an action transform block, and it takes an initial actor representation, full image features, and sort of does attention over that and gives you an updated representation. And basically the idea is very similar to what transformer architecture is from the language domain. Yeah.
So when you do this attention, what are the elements of your set over which you're attending? Are they just
every spatiotemporal feature value. So basically, we're basically attending over each of these positions.
I see. So have you also tried? So you already have region proposals.
Right.
Have you tried attending only over region proposals?
We tried adding that as well. That did not help. But no, we didn't try just using our region proposals. So there is actually some concurrent work on doing region proposals and building like a graph network on top of those, which is also concurrent, which seems to also help. So I mean, I wouldn't be surprised if that also works pretty well. But yeah, to simplify, we just use the whole feature map, so we don't have to sort of be limited by a region proposal. We can attend over everything. And so the important thing is the dimensions of the actor representation and each of the spatiotemporal locations is exactly the same. So we can just attend over all of that. Okay. So now that we have this spatial action transformer block, we can plug it back into a relational architecture. So the initial part remains all the same. We have the feature initial spatiotemporal features, RPN, ROI pool. That gives us the initial actor representation. And now we have these transformer blocks that take the initial representation, the full video features, and basically compute an updated actor representation. So just the way it's all set up, because it gives you an updated representation, we can sort of stack these in multiple heads and layers. So basically, multiple heads would each give you an updated representation that we concatenate, and then we can pass it through another layers of these transformer blocks. So again, this is also very similar to the way original transformers are implemented. Each of these layers can sort of be thought of as learning different ways of doing attention over the original features. And once you have the final updated representation, we can pass it through, again, a classification regression loss, same as faster RCNN. And this is our new architecture. And basically, the head, what has changed is that instead of having that 3D convolutional head, now we have this transformer head, which we call action transformer. And now we'll experiment with that. So the first experiment is just comparing it to our baseline model, which was already quite powerful. And for the first experiment, let's just consider the case where we have ground truth boxes are known. So we are only evaluating the recognition performance and assuming the detection is already solved. So if we, in our baseline, if we assume the detection is solved, we get a small 2% improvement, which actually shows that detection is not really the hard problem on this data set. So recognition is the main problem. And now if we add the action transformer head instead of the 3D convolutional head, we get a pretty significant, like 5% boost over our baseline model. So which was quite encouraging given that our baseline model was already pretty strong. Next, putting both the things together, both detection and classification. So the too many numbers here, but basically what I'm showing is compared to our baseline model, we were able to get about a 4% improvement overall using by adding our transformer architecture. And then we can also compare to state of the art. Again, too many numbers here. The only thing is, compared to previous published state of the art, it was almost 7.5% better. And compared to all the challenge submissions, it was about 4% better. And yeah.
Yeah, so transformers generally end squared and the input in sentences aren't too long. And I imagine the number of keyframes and regions and all these things are quite many. How slow is it?
So yeah, exactly. So transformer will be n squared, but the one advantage we have is now we have person regions that we are interested in. So instead of doing all pairs attention, now we only are doing attention for each of these people. So that sort of reduces that one side to be much lower. So there is actually previous work. There's non-local neural networks, which is actually doing exactly what you say, like comparing everything to everything, which does sort of blow up all the computation. But in this case, we can actually reduce it down by just looking at the people. So people are queries in the transformer sense of things.
And if you were jointly doing the people and the actual activity recognition, then you get that blow up.
Yeah, so the advantage here is that we are only interested in every individual person's actions. So we are not trying to classify the video as a whole, but a person specifically. So we only need to do that person's attention over the whole video. So we are limited to the number of people we are considering, which is typically a small number, like 64 or something. Okay, so we can also visualize what the model is learning. So so we can first look at these key and value projections. So these were just linear projections of the original video feature. And here I'm showing all the projections. So I'm showing the feature representations converted to 3 dimensions using PCA and then color coded. And I'm showing it for all the 2 heads and 3 layers that we have. And if we just focus on like 2 of these and sort of look at these, what we see is the model sort of learns to track people over time. So what we are seeing here is these green blobs that are basically tracking the people as they move. And what's more interesting was that we saw one of these layers ended up sort of tracking people in a semantic sense. So all the people were projected to this green embedding, so all the people in the same embedding. And then another one was sort of more instance level, where every person was embedded in a different color, but they were still being tracked. Yeah.
Could you explain again how you got these visualizations? What
So,
features are you using?
so we are taking these. So we basically have these key and value projections. So these are basically just linear projections of the original video feature. So these are 128 dimension for every spatiotemporal location. We project that down to 3 dimensions by PCA and just color code it RGB for these 3 numbers, and then we visualize those.
This is attention given which person?
So this is independent of person, because this is just the original embedding. So this embedding is independent of people. The attention value I'll show next is actually dependent on the person. Yeah, so exactly. So we can also visualize the attention values, and this is specific to the person. So the person is being shown in the box, and it so basically learns to look at other people, sort of objects in the scene, and sort of focuses on hands and faces, which are usually more important for recognizing actions on this data set. And these are just the final predictions of the model. It works pretty well on most of the common actions, though of course the overall performance is pretty low at 25%, so there is still a lot more work to be done. Okay, so this was sort of the first part of this talk, trying to encode context and recognizing people's actions. And what I've talked about is using actors as a means to pick out regions in the video that are useful for recognizing that person's actions, and using that to build a actor representation. Okay, so with that, I'll talk about the next part, which is trying to predict what can happen in a scene. So the setup here is that so we are given an image, and we are already pretty good at recognizing what people are doing, but we can do more than that. So we can predict what can somebody do there. So for example, we can say that somebody can possibly stand next to Sheldon because there's like a floor there, so somebody can stand there. We can also predict somebody can sit in that sofa next to Penny. And basically this is the idea of affordances. And this was originally defined by J.J. Gibson as sort of opportunities to interact with the scene. And you can think of this as sort of ways of trying to come up with a representation for the scene on how can people possibly interact with that scene, which can be useful for a lot of downstream tasks like robotics, for instance. If somebody is trying to help somebody sit somewhere, they need to know that sofa is a sittable place, and not, let's say, a stovetop or something. Okay, so the way we define, so just to sort of narrow down the specific task that we want to solve, is that we are given a scene and a position in that scene, and we want to predict what possible actions a person can do at that position in that scene. So for example, if we give it the sofa and a position on the sofa, we want to say that somebody can, for example, sit there. Another example could be the supermarket scene. Given a position there, we want to predict that somebody can sort of be standing, reaching out to the counter to pick something.
Is the input just a point?
Yes. So we parameterize. I'll talk about how we parameterize the point, but yeah, it's just a point and an image. Okay. So how do we do that? So since there is no existing data set to do something like this, one option is we go ahead and label one. So in a semantic segmentation style, we label walkable surfaces, drawable surfaces, hittable surfaces, and then we can sort of place humans in poses that sort of conform to those actions and just place them in the scene. So that's one option. But obviously, this is very expensive and unscalable, and also it's sort of limited by the imagination of your labelers. So for example, a labeler may not think that, for example, that ledge is sittable, but somebody can, for example, sit there. Another option is that we go ahead and do full 3D understanding of the scene. So this is actually something I've worked on a little bit, where I sort of worked on going from single images to predicting full 3D structures. And so once you have a representation like this, you can actually try to place humans on top of these 3D representations. So this is basically just taking human poses and trying to fit them into the 3D scene that you have, and try to see all the possible poses that can exist. And in fact, there has been some previous work in doing things like that. But also, this is also not quite ideal because, for example, all flat surfaces may not be sittable. So even though you can think of a stovetop, for example, to be sort of at a sittable height, but you don't want somebody to actually sit there, even though it's a flat surface. So instead, what we propose is watching TV to learn these affordances. And basically, the idea is that our algorithm looks at a bunch of TV series and tries to learn about these affordances by using the fact that these TV series typically have a small number of scenes that are interacted by a whole bunch of people in a bunch of different ways over the different episodes and seasons of this TV series. So to put it more concretely, this is the sort of data set that we are able to collect out of this TV series. So what we are seeing here are individual frames from the TV shows, and they have been labeled by the ways a person can exist in that scene. So for example, people can sort of sit out on a sofa, People can sit on a sofa in a different sort of in a cross-legged way, for example. People can even sit on the floor, for example, here. And this is all being collected automatically in a method I'll talk about in a minute. But basically, we're able to collect all of this data that can then be used to learn a model to go from scenes to predicting possible affordances in given that scene. So the way we do it is we first start by finding these frames from the TV series that are empty or basically don't have people in them. We just train a classifier to find these scenes, and then we do a nearest neighbor lookup over all the different frames from the TV series to find other frames with the same scene from the same viewpoint but with people in them. And once we have those different scenes, we can basically just detect people, extract their pose, and just transfer that onto the original frame that we had, which was empty. And this gives us like one data point of this scene labeled with a bunch of different actions that a person can do in that scene. And another way of doing this is what we refer to as local matching. So instead of doing a full nearest neighbor lookup, we first find sort of short video clips that sort of just do short detection to find shots which have people interacting with the scene, and we can just take one of the empty frames and just transfer all the people into that frame. So for example, here you can see somebody sort of walking through a hallway. And now that we have this data set, we can actually basically learn a model to predict this in a novel scene. And the setup is again the same. We are given a completely new scene that is not from this TV series or not something we have trained on, and we want to, given a point, predict what actions that can happen there. And again, just to reiterate, obviously we cannot do this traditional pose estimation because you don't actually see a person there. So if you ran a pose estimator, it'll give you some crappy output. And I'll skip over the actual details of the model for the time, but basically we have like a generative model which takes the frame, a point in the frame, which we parameterized by sort of different crops of the scene at that point, and basically train a model to predict sort of a distribution of poses that can exist at that point. And this is trained using the binge watching data set that we collected just before. And here are some examples of the results of this model. So this is evaluated on a held out TV series. So we basically have 7 TV series, and we use 6 for training and the last TV series for testing. So these are scenes that the model has never seen before. So these are not just trained tests, so these are completely new scenes for the model. But as you can see, it generalizes fairly well. So it learns that people can sort of sit on beds, reach out to like switchboards, and sit on sofas, and so on. And note that no semantic information is being used here. We're not doing any object detection or anything. Completely from pixels, it's directly able to predict what possible actions people can do. Yeah.
So one of the problems I can see with using TV series,
Mm-hmm.
a lot of these are sitcoms.
Mm-hmm.
Sitcoms are generally shot on setting.
Right.
So there would be a limited number of furniture pieces, scenes,
Mm-hmm.
ways of interacting with them, etc. So have you done any analysis on what's the diversity of scenes or furniture pieces or places in the scene? And
Right.
if that's affecting your generalization at all?
So we do have some analysis. We do some quantitative analysis of how our performance changes as we add more TV series. So we do have. So I think we use 6 TV series at training time, and we get a pretty diverse set of scenes from that. So of course there's no limit to how many we can add. That was just the set we worked with, but you can pretty much extend that to as much you want. So we do get an improvement as we add more data. So I was going to skip this, but basically the way we do this evaluation is we on the held out TV series we will we also label it in the exact same way, and at the points where we have poses we will try to use our model to predict the pose and then see if our prediction is within the top 5 of what we labeled or not. And what we see is that adding number of training frames we do see an improvement, but yeah, of course, I mean, so we don't have a sort of there's no like a universal ground truth here on we have solved this 100% or 80%. So this is sort of still a very pseudo sort of analysis or evaluation. So yeah, I mean, it's very hard to do like a very clean evaluation in a setup like this. Okay, and yeah, we also have some results on completely different data. So these are NYU V2 images. So these are obviously not from a TV series. and it seems to generalize reasonably. It sort of learns people can sit on the bed and so on. Okay, so that was the sort of second part of the talk, which was trying to use this trying to use TV series to learn a mapping from going from context directly to predicting possible actions that can happen in that scene. And with that, I'll try to like to move towards encoding long-term temporal context. So in the first two cases, we have tried to encode context, but it has been mostly either spatial context or temporal context on like short video clips in the first case. But obviously videos are much longer, and ideally we want to be able to encode all of that in order to recognize actions or do video understanding in general. All right, so the first question is, why haven't we already figured out temporal and long-term reasoning? Video action recognition has been a problem for many, many years. And I think one of the, and obviously the data sets have gotten larger over the years and more complex, from KTH, which was like simple 6 actions by human actors, to things like kinetics, which has like hundreds of classes and a very complex YouTube videos. But the problem is that even on these more and more complex data sets, some of the simple methods have still been sort of state of the art, or they have easily been able to solve most of the tasks that you define on these data sets. So for example, from 2Stream to 2Stream i3D, which was in 2 years back in CVPR, and even the non-local network, which was state of the art on kinetics, they're only looking at short video clips. So basically they take the whole video, chop it into short clips, and just do recognition on each of these clips and sort of average the predictions in the end. And even something like that is already getting like 80% performance on kinetics, which was just proposed like a couple of years back, and it's already close to being solved. And so basically the problem is that these simple methods have been easily able to solve these data sets without actually needing any long-term temporal reasoning. And if we look a little bit more closely, the problem is even more dire, I would say. So for example, so here I'm showing some of the 3D and 2D convolutional models. So basically 3D convolutions are spatiotemporal convolutions, which sort of model some amount of temporal aspect of the video. 2D convolutions is obviously a frame-by-frame predictor, which just looks at individual frames and averages predictions. And what we can see is on kinetics, even that 2D model is sort of close enough to these 3D models. And what that means is basically just looking at frames is good enough to do pretty well on sort of modern video action recognition tasks. And in fact, this one result from ECCV18 was even more telling, I think, where they actually took the kinetics model and sort of tested it on videos that were reversed. So you just run the video reverse in time, and they actually get the exact same performance. So what that means is that even the temporal evolution of actions doesn't matter. All you need to see is the frames, and that's good enough to recognize what action is going on. So temporal ordering does not matter. So does that mean we can ignore the temporal aspect of videos? I don't think so, because if I show you this clip, so this is this is a clip from The Godfather, one of my favorite clips, and what we see here is the protagonist sort of extracts out a firearm from behind a bathroom stall, and sort of walks out, and in a second we'll see he sort of goes out to his companions who are sitting there and eating. And in this clip, even though we only see the gun and the in a few pixels in the initial part of the video, we can sort of reason about object permanence, and we know that the protagonist actually has the gun in the last frame. And using that, we can also sort of estimate the intentions of the protagonist, that he's probably planning to shoot one of these people. And reasoning like that requires reasoning over the spatiotemporal extent of the video. You cannot just look at individual frames from this TV series, like sample 25 frames, and try to come up with an understanding like that. And even simpler instantiation of something like this could be the cup and ball shell game. And so the setup here is you have a bunch of cups, and you have a ball under one of these, and then somebody basically just shuffles these cups around. And the task at the end is that you want to recognize which of these cups has the ball under it at the end. And even cats are able to do that, but obviously our video models cannot, because video models are just looking at a bunch of individual frames sampled uniformly, and a setup like that will obviously, there's no way it can solve a task like this. And that sort of inspired us to come up with this new data set called Cater. And this is something I've been working on most recently And basically, the idea is very similar to sort of the Clever dataset, which was originally proposed for reasoning in images, except now we have a temporal aspect to it. So we basically have this almost the same objects we had in Clever, but now we also add actions on them. So basically, each of these objects now affords a bunch of different actions. So things like picking and placing, sliding, rotating, and so on. And then we define a bunch of different tasks on this data, which I'll talk about in a minute. And those are by design sort of spatiotemporal reasoning tasks. And you cannot solve those tasks by just looking at individual frames. And since it's a synthetic data set, we can control number of objects that are moving, add camera motion, and so on. So all of this can help us sort of debug video models and things like that. All right, so in terms of tasks, the first task we define on Skater is very simple, sort of a debugging task. It's atomic action recognition. So we define all the actions that are happening in the scene, and the task is to sort of classify all the actions that are actually happening. So there are 13 sort of atomic actions on this data set, and basically the task is just to classify which of these were actually active in that video. And it's a very simple task. Almost all models solve it. Mostly just a debugging task. And you can evaluate that using multi-level classification using MEP, which is pretty standard. The second task, which actually requires a little bit of temporal reasoning, is compositional action recognition. So here you need to predict what all compositions of actions that are happening in the scene. So you have to predict that, for example, pick and place of snitch happened before pick and place of cone. So that golden thing is what we call a snitch. So basically, you have to reason about sort of temporal ordering of actions, like things that happen before something, things that happen after something, or during something. And of course, before and after can be arbitrarily before and after. So for example, something could have happened in the beginning and something else could have happened in the end, and you still need to be able to predict that that actually happened in this video. And then finally, sort of the most interesting task on this data set is what we refer to as snitch localization. And snitch is that golden thing, and the task is that you have to classify where that snitch is at the end of the video. And again, we set it up as a very simple classification problem, where we sort of make a grid on the floor, and it's a 6x6 grid, so it's just a 36-way classification problem. And yeah, so you just have to classify which of these blocks my PowerPoint died for some reason. 1 second. Okay. You just have to classify which of these blocks has the snitch at the end of the video. And while it might look trivial from this simple example, it does get quite hard because the snitch can actually be contained by other objects. So for example, this cone object has this containment operation that it can contain smaller objects. So in this video, the purple cone first contained the snitch, and then the gray cone further contained the purple cone. And so these objects can be recursively contained and sort of moved around, and you need to be able to sort of reason about all of that in order to actually predict what the final location is. And so given these tasks, we experiment with all the baseline models. So 2D models, 3D models, even the most recent non-local model, which are all state-of-the-art on sort of kinetic style data sets. And we experiment with sort of the standard aggregation. So all of these models work on short clips, as I said. So over a video, the typical way of aggregating the belief is by just averaging over all these short clips. And we also train an LSTM, which is not typically used, but since our task is more sort of temporal, we also experiment with that. And here are some results on these tasks. So the first task was atomic action recognition, a very simple task. Almost all models are able to solve it perfectly. So we could get almost like 100% accuracy. Adding camera motion does make it a little bit harder. But this is what we expected. This was a simple task, so it's easy to solve. Next was the compositional action recognition, where you need to reason about ordering of things. And here we do see the performance is quite a bit lower, so close to like 50% MAP. And here we actually do see an improvement by going from average pooling to LSTMs, because hopefully the temporal modeling is actually useful here. And then finally, sort of our main snitch localization task. So here we do a much more comprehensive analysis. So we experiment with 2D models, and what's interesting to see is that 2D models actually work pretty bad. So the performance was almost like 14% or using RGB, 10% using flow, which is interesting because in a lot of existing data sets, 2D models work almost as well as 3D. So we are actually coming up, our task is actually more temporal. Flow did not help. So this is another interesting thing. On a lot of existing data sets like HMDB, using flow for recognition is actually works better than RGB. But of course, in this setup, you cannot just use optical flow to recognize actions. LSTM again helps a little bit, and overall the performance was quite a bit lower than sort of existing data sets. So the goal was that hopefully we come up with a task which is actually hard for video recognition models. Yeah.
So what percentage of scenes was the snitch actually visible in the last position?
Good question. So we actually have that analysis too. So we can actually analyze. We can do all that kind of analysis on where snitch was visible and not visible. So basically the green bars here are actually showing the percentage of data where snitch was in this case visible and the second case not visible. So about I would say like 35% or something of the data it was not visible, and we actually see. So here I'm showing the performance on the subset of the data where it was visible and not visible, and we can see that the performance actually drops if the snitch is not visible in the end. Yeah.
Did you train a image only base or like no time baseline where you only take the subset of data which has the snitch visible at the end as the training data?
No. So we do have an image only baseline. So these are 2D models. So these are frame by frame prediction.
Yeah, but like you could take the last frame.
Mm-hmm. Right.
And for a single frame model, if the snitch was visible, you should be able to know where the snitch is as accurately as you can do an object.
Yes. So we right.
Pretty accurately, right?
I think so. Yeah. I think that shouldn't be hard. So I mean I don't have that number, but my guess is that should just work at 100%. Like
So then it seems like a single frame baseline should at least have 60% of the time it's visible.
I see. Okay. So okay. So the reason this thing also does get worse is because there's this averaging operation. So I guess so the averaging comes from like standard action recognition setups where you take a bunch of these clips and then you average the predictions, and we basically use the baselines as they are, like without actually sort of modifying them for our setup too much. So yeah, I mean.
Like, but I mean, if the claim is the dataset really needs temporal, right? So it's 60%
Right.
of the time you know it doesn't need temporal.
I see. Okay, so I guess that's so the reason 60% of the time it does not need is because we completely randomly generate the data, but we can sort of only collect the data set where it's actually contained in the end. So that's totally doable. The way we generated it, we did it completely randomly, but we can obviously make like an adversarial data set which is actually hard, and sort of evaluate things in that setup. Yeah.
The other question is, how many unique camera positions are there? Is it fairly continuous, or is it?
So we have two setups where camera is fixed, and the other one where we have I think 8 locations, and it just moves between those 8 locations, and we sort of put some constraints so there is no like jarring change in viewpoint. Yeah.
So another random baseline that's interesting. Could you go back one slide, please?
Yeah.
So here, when you say random baseline, you're just saying pick a location randomly.
Yeah.
36.
Right.
But in fact, a much easier, a stronger baseline, which is still very trivial,
Mm.
is pick a location amongst the ones containing objects, because that should be trivial for any network to do. Saying you have a gray background, right? of some kind.
Right.
So it's never going to be a location, 36 locations that have the gray color. It's going to be one of these other locations.
Right.
Just to get a sense of what are your image models doing. If
Sure.
there's only 7 locations with objects in them on average in the data set, then that's what I'm
So-
going to assume that's what your static model with averaging is doing.
Right. So I think so we do try to do. The reason we do it randomly is we try to make sure it's like uniformly distributed. Like ideally everything, like all positions should be equally likely. So ideally it should be, the random should be like 2.8 or whatever. Like
No, what I'm saying is that for a given video, the
Sure,
task
okay.
of just doing like objectness
Right.
is very easy, and these models should be able to do it given the synthetic nature of the video.
Right. Right.
So, given that you can detect all the objects,
Mhm.
let's say 100%,
Right.
what's the new random now? It's only one of amongst those locations. So it might be interesting to see if
Right.
what that number is. Which
Sure,
will
sure.
reveal what these networks might be doing.
Sure. Yeah. 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 That's a good point. We don't have that, but yeah, I think that makes sense. But yeah, I think having this synthetic data, that's the power that you can actually sort of analyze all these different things that you probably cannot do in like a real world data set. All right, so just quickly finishing that. So yeah, this was sort of a data set trying to move towards longer term reasoning and try to come up with some tasks which are which truly require temporal reasoning and hopefully cannot be solved by looking at individual frames. All right, so with that, I'd like to quickly talk a little bit about sort of future work and things I'm working on right now. All right, so I started off the talk with sort of motivating, or this was sort of one of the motivations that you want to recognize these more atomic actions because they are usually easier to recognize from individual images and videos. So going forward, I would like to try to move this towards being able to recognize these even longer term actions or being able to reason over longer time periods. And in fact, sort of the last work on Cater was sort of like a step towards that. Because a lot of video understanding has sort of been limited to these individual short-term actions, and we as humans can reason over long time periods, and ideally we want machines to be able to do that too. And since this looks like a pretty hard problem, but we can try to sort of narrow it down. So sort of one concrete example of a task, of a long-term reasoning task could be, for example, if I don't know why the video is not playing, but if I show you this movie and ask you questions like, at what point did anyway, at what point did why did Michael kill those people, or what point did Michael decide to turn into a criminal? So anyone who has seen The Godfather would have the exact same answer. So it's not an ambiguous task, but at the same time, video models or current state of video understanding will obviously not be able to solve this sort of long-term reasoning problems. So that's sort of one sort of concrete setup of a long-term reasoning problem that I think is very much unexplored and I think would be very interesting to solve. And as I said, that existing work is very much short-term, trimmed, and acausal. It looks at future and past and try to recognize what's happening in the middle. So towards this long-term reasoning, there are some potential first steps that one can sort of work on, which I think are would be very useful. So things like sort of search and retrieval of certain actions. So the setup here is you're given a video and you want to recognize, or you want to find instances of some specific actions that you're interested in. So like some sort of zero-shot recognition or low-shot recognition. So sort of coming up with classifiers given a natural language query and trying to find regions or temporal instances in the video which are actually where that action actually happens. So again, this is a very nicely evaluatable problem. You can easily label data and everything. And also another way of sort of doing language and videos is also video question answering. So given a question, trying to answer what's happening. And in fact, in the second part, I've done a little bit of work, and this is basically the setup is something like this. You're given a video, you have a question, and you have a bunch of options, and you want to answer these. And for example, in this setup, in this video, to answer what room was Wilson breaking into and house found him, there are quite a few sort of interesting problems one will have to solve to sort of be able to answer things like these. So things like entity resolution, like who is Wilson, whose house potentially. Of course, the semantic activity recognition. What does it mean to sort of find somebody? And then, of course, sort of scene understanding that that scene is of a kitchen and not a living room or something. And actually, I've been mentoring like a master student on some initial work in this direction, and we actually worked on the movie QA dataset, which is an earlier version of the TV QA example I showed earlier. And on this dataset, we were actually able to get state-of-the-art performance using a QA only model without actually looking at videos. So, which is a little depressing, but hopefully the newer datasets are sort of solving those issues. There are a lot of biases in these datasets, and I think it's important to be sort of cognizant of that. So this is one direction that I'm interested in, sort of language and videos. Another direction that I find quite exciting is sort of using these videos to learn skills. So for example, looking at a bunch of videos and trying to transfer that to, for example, a robot or a simulation. I think the idea here is that there's a Chinese proverb that you see, forget, or you hear, forget, I see, I remember, and I do understand. I think the true, sort of the true evaluation of video understanding would be if we can see a bunch of videos and actually affect that same change in the environment that we see in the video in sort of in real world or in simulation or things like that. And another random direction that I've very recently been working on is sort of this video translation, and we're trying to use some sort of temporal reasoning to do that. And basically, the task is you are given a video and you want to translate into another person doing the same actions. This is also very initial results. I'm mentoring an undergrad in this direction. And I think a lot of these directions have, there are a lot of related projects I've been looking at AI too, which are quite related to things I've been working on. So things like charades for video understanding and temporal reasoning, sort of 3D and physical understanding of scenes, and also like Thor, which is, I think, a very useful environment for being able to actually learn from videos and sort of affect those changes in the environment, for instance. And yeah, with that, I'd like to quickly thank all my collaborators without who all of this work was not possible, from the various different organizations. The code for most of these papers I talked about are on my GitHub, so you can feel free to check that out. And with that, I'd like to thank you for your time, and I'm happy to take any questions.